Hello, how are you doing? Hope you're doing well. You're enjoying these lectures. I'm enjoying doing them. The highlight of my day. Now, I want to talk about this thing called the ratio test. But before I do that, I just want to just give you a couple things for the direct comparison test. These are common series for comparison. I'll spell comparison correctly this time, I think. Beautiful. So this is still in section 10.3, but this is just a little supplement for it. When you're comparing, trying to see if a series converges, and you can compare it to a couple things, and it's good to know which series will definitely converge. Well, the geometric series it will converge, not always. It will converge for absolute value of r less than 1, and it will diverge if absolute value of r is greater than or equal to 1. Okay? So if you can compare your series to a geometric series, you can maybe get some information out of it, especially if it's less than one that converges, then it converges. I think this, it doesn't really have a name. So the series that it converges. So 1 over n factorial converges. And then this thing I'm calling the p-series. And hopefully in the homework, this is and the sum n equals 1 to infinity of 1 over n to the p power. This will converge if converge for p greater than or equal to 1, and it will, no, sorry, it's the other way around. It will converge, oh no, I had it right. It will converge for p greater than or equal to 1, and it will diverge if p is less than 1. All right, and that's just a good it will not converge, I'm sorry. It will, it'll converge not for p equal to 1. I was thinking ahead of myself there. All right, so, but it will diverge for p less than or equal to 1. Okay, and that's just good for direct comparison. All right, what I want to talk about now is the ratio test. So this is 10.3 infinite series. And this is the ratio test. And this will probably take 2 films, just because I've already spent so much time on that direct comparison table. All right, so the ratio test is pretty straightforward, and you know, the gist of it is as follows. What we want to do is compare consecutive terms in a series. So, you know, let's look at an example. Okay, so we're gonna consider some series. Consider a sub n, or the sum. Okay, and what we want to do is we want to see what the value is of a sub n, of the nth term as n goes to infinity. So we're going to take the limit as n goes to infinity of the ratio of a sub n plus 1 divided by a sub n. All right? So this is the ratio of consecutive terms near infinity. So we're not looking at what the ratio of the sums are. This is the ratio of the terms that we're adding on. All right. So basically, this is seeing if the a sub n plus 1, as n goes to infinity, if that is smaller than the a sub n, all right, then we're in good shape. Okay. And the book gives a name for this ratio, so I'll use it. Well, I don't know. Let's just call it rho. I don't want to call it r because that's so we'll call it this Greek letter rho. Rho. All right. So if rho is less than 1, that means that the series converges. If rho is greater than 1, that means that the series diverges. And if rho is equal to 1, the test is inconclusive. All right, so let me just apply this to one example, and then that'll be the end of this film. So what we're going to do is, well, let's consider the series, this series. So consider say the sum of 1 to infinity. What is that? 2 to the n plus 5. So this is n equals 1 to infinity of 2 to the n plus 5 over 3 to the n. All right, so that's 2 to the n plus 5 all over 3 to the n. Now, sort of the dominating terms aspect should kick in here. I don't think it should be hard to realize that this series converges without doing a test. All right, because the 5 becomes irrelevant as n goes to infinity. So you're really just dealing with 2 to the n divided by 3 to the n, which is the same thing as 2 divided by 3 to the n power. and 2 divided by 3 to the n power is a geometric series with r less than 1. Alright, so yeah, the series converges, and let's show it with the ratio test, because this isn't a geometric series per se, but let's apply the ratio test. So we want to find rho. Rho equals the limit as n goes to infinity of a sub n plus 1 divided by a sub n. So a sub n plus 1 equals 2 raised to the n plus 1 plus 5 divided by 3 to the n plus 1. So the ratio a sub n plus 1 divided by a sub n is 2 to the n plus 1. I'll write this out in for big, could be a mess. 2 to the n plus 1 plus 5 divided by 3 to the n, and all that is divided by 2 to the n plus 5 divided by 3 to the n. A mess. Dividing fractions is easy as pie. You flip the bottom and multiply. So we get 2 to the n plus 1 plus 5 divided by 3 to the n plus 1, and all multiplied by 3 to the n divided by 2 to the n plus 5. 2 to the n plus 5. All right, so let's keep calculating that. And really, I can, since multiplying fractions, I don't have an order of multiplication here. I can switch these. So I'm going to combine the 3 to the n. So this is 3 to the n divided by 3 to the n plus 1, and all multiplied by 2 to the n plus 1 plus 5, all over 2 to the n plus 5. Well, if n is, say, 10 or something like that, then I'm going to have 3 to the 10th over 3 to the 11th, or 3 to, whatever, the numerator is going to have one more 3 in it, or the denominator is going to have one more 3 in it. So this first one is just 1/3. Now the second one's a little trickier, I suppose. I think what I would do is get that 2 out of there. When we split this up, we'll get 2 times 2 to the n, all plus 5, divided by 2 to the n plus 5. Alright, so the 1/3 should be, what we're going to do now is take this limit. I don't even know if we needed to break that up. But the limit as n goes to infinity of 1/3 times 2 to the n, or 2 times 2 to the n plus 5, divided by 2 to the n plus 5. Well, the plus 5 is irrelevant. So as n goes to infinity, this is just going to be 1/3 multiplied by 2 times 2 to the n over 2 to the n, and the 2 to the n's cancel out, and this is just 2/3. Alright, so what we have out of this is that rho equals 2/3. So that just means that the terms are all getting smaller, right? The consecutive terms are getting smaller. So what I'm adding each time is less and less and less, and in fact, it's getting less. So this is at infinity. The ratio is 2/3. So this implies that this series converges. Let's see, write that down. That's a horrible sigma. This implies that n equals 1 to infinity of 2 to the n plus 5 all over 3 to the n converges. We don't know where, doesn't matter. Okay, it doesn't converge at 2/3 or anything like that. It's probably some monstrous value, but it doesn't matter what it is. The fact is that that series converges because as I take the ratio of consecutive terms close to as n goes to infinity, I get a ratio of consecutive terms that's less than 1. All right, so that's the beginning of the ratio test. I'll probably do one more little lecture on the ratio test, or maybe some more example, especially one that for which the test is inconclusive. So I hope you enjoyed this, and good night and good luck.